Welcome to a new chapter of our course. This week, we begin Chapter 2, Systems of Linear Equations. In this chapter, we will study how several linear equations can be combined into a system and solved simultaneously. We will first review the basic concepts and types of linear systems. Then examine the existence and uniqueness of solutions and common solution methods. Finally, we will apply these techniques to several economic and business models, such as market equilibrium, input-output analysis, macroeconomic equilibrium, and the IS-LM model. By the end of this chapter, you should be able to achieve 4 main learning objectives. First, formulate and identify general and special systems of linear equations. Second, determine whether a linear system has a solution, and whether that solution is unique. Third, solve systems of linear equations using appropriate methods. And finally, apply linear systems to practical problems in economics and business. These objectives will guide the topics and examples throughout this chapter. 2 main learning materials are used. The first textbook is the book Basic Mathematics for Economists by Peter Lee and Mike Rosser. The second book is the book Advanced Mathematics for Economics by Ladin Thuy. Volume 1 and 2. We now begin the first section of this chapter, Systems of Linear Equations. A system of linear equations consists of 2 or more linear equations involving the same set of variables. In this section, we will learn how to write a linear system in general form, identify different types of systems, and represent them using matrices. This foundation will help us analyze whether a system has a solution and prepare for the solution methods introduced in the next sections. We begin with the general definition of a system of linear equations. A system consists of m linear equations involving n unknown variables, x1, x2, xn. In each equation, the numbers a, I, j are called the coefficients. The first index, I, identifies the equation, while the second index, j, identifies the variable. The values b1, b2, bm on the right-hand side are called the right-hand side constants. So, in general, a linear system may contain a different number of equations and unknowns. Our goal is to determine values of the unknown variables that satisfy all equations simultaneously. Instead of writing all equations separately, we can represent the entire system in a much more compact form using matrices. The system can be written as AX equals B here. A is the coefficient matrix containing all coefficients of the system. The vector x is the variable vector, containing the unknowns x1 through xn. And b is the right-hand side vector, containing b1 through bm. Notice the dimensions. Matrix A has order m by n, while x has order n by 1. Therefore, their product has order m by 1, which matches the dimension of b. This matrix representation will allow us to use the matrix techniques developed in Chapter 1. From the matrix equation X equals B, we introduce another useful representation, the augmented matrix. The augmented matrix is obtained by placing the right-hand side vector B as an additional column to the right of the coefficient matrix A. We can read the notation as A augmented with B, or simply, A bar B. If A has m rows and n columns, the augmented matrix has m rows and n plus 1 columns. The vertical line is only used to visually separate the coefficients from the right-hand side constants. The augmented matrix will be particularly useful when we apply elementary row operations to analyze and solve a system. Let us apply these definitions to a specific system with 3 equations and 3 unknowns. We first construct the coefficient matrix A. The first equation gives the first row, 1, 3, and 2. In the second equation, x2 does not appear, so its coefficient is 0. Therefore, the second row is 2, 0, -1. The third row is 3, 1, and 6. Next, the variable vector contains x1, x2, and x3. The right-hand side vector contains 5, 2, and -4. Therefore, the original system can be written compactly as X equals B. Finally, by adding B as the last column of A, we obtain the augmented matrix shown on the right. An important point is that a missing variable in an equation must be represented by a zero coefficient. Now that we know how to represent a system, we need to define what we mean by a solution. A vector X is a solution if, when substituted into the matrix equation, it satisfies X equals B. In other words, its components must satisfy every equation in the original system at the same time. The collection of all vectors satisfying the system is called the solution set, or the general solution. A system may have one solution, infinitely many solutions, or no solution at all. We will distinguish these cases shortly. The slide also introduces the rank of the system, which is defined as the rank of its coefficient matrix A. This connects the current chapter directly with the concept of matrix rank studied in Chapter 1. We now introduce two special types of linear systems. First, a system is called homogeneous when every right-hand side value is 0. In matrix form, this is simply X equals 0. If at least one right-hand side value is non-zero, the system is called non-homogeneous. One important property of a homogeneous system is that it always has at least the zero solution, where all variables are zero. The second special case is a Kramer system. A system is called a Kramer system when the number of equations equals the number of unknowns. So the coefficient matrix is square, and its determinant is non-zero. Because the determinant is non-zero, the coefficient matrix is invertible, and the system has a unique solution. We now address an important question. Does a system actually have a solution? If a linear system has at least one solution, it is called consistent. If it has no solution, it is called inconsistent. To determine this without solving the entire system, we can use the ranks of two matrices. The theorem states that a system X equals B is consistent if and only if the rank of the coefficient matrix A is equal to the rank of the augmented matrix A bar B. So the practical rule is, equal ranks mean that at least one solution exists. Unequal ranks mean that the system has no solution. Later, we will also compare this common rank with the number of unknowns to determine whether the solution is unique or infinite. We have already learned how to determine whether a system is consistent. The next question is, if a solution exists, is it unique? The answer depends on the ranks of the coefficient matrix and the augmented matrix, together with the number of unknowns. There are three possible cases. First, if the rank of the coefficient matrix is different from the rank of the augmented matrix, the system is inconsistent, so there is no solution. Second, if the two ranks are equal and also equal to the number of unknowns n, then the system has a unique solution. Third, if the two ranks are equal to some number page but p less than n, then the system has infinitely many solutions. In this case, there are n-p free variables. So, the key comparison is, compare the two ranks first, and then compare their common value with the number of unknown variables. Let us return to the previous example and apply the theorem. For this system, the coefficient matrix is A1, and the augmented matrix is A1 bar B1. We have already determined that the rank of A1 is 2, while the rank of the augmented matrix is 3. Because these two ranks are different, the consistency condition is not satisfied. Therefore, the system is inconsistent, which means that there is no solution. Notice that we do not need to solve for x1, x2, and x3 directly. By comparing the two ranks, we can determine immediately that no vector can satisfy all three equations simultaneously. This example illustrates the first case of the theorem. Unequal ranks imply no solution. For a Kramer system, the coefficient matrix A has a non-zero determinant, so A has an inverse. We start with the matrix equation. Ax equals B. Now multiply both sides by inverse. So we have A inverse times A times x on the left-hand side equals A inverse times B on the right-hand side. Because A inverse times A equals the identity matrix, the left-hand side becomes simply x. Therefore, x equals A inverse times B. So, to find the unique solution, we first compute the inverse matrix A-1, and then multiply it by the right-hand side vector B. This is another direct method for solving a Kramer system. We now move from checking the existence of solutions to one method for actually finding the solution. For a Kramer system, where the coefficient matrix is square and its determinant is non-zero, we can use Kramer's rule. First, calculate D, the determinant of the coefficient matrix A, to calculate D1. Replace the first column of A with the right-hand side vector B and calculate the determinant. Similarly, D2 is obtained by replacing the second column with B, and we continue in the same way up to Dn. The solution is then obtained from x1 equals D1 divided by D, x2 equals D2 divided by D, and so on, up to xn equals Dn divided by D. The main point to remember is that each variable corresponds to replacing its own coefficient column by the right-hand side vector. Kramer's rule is convenient for small systems, but for larger systems, other methods are usually more efficient. Another important and more general method for solving linear systems is the Gaussian elimination method. This method is based on elementary row transformations. First, form the augmented matrix, A bar B. Second, use elementary row operations to transform the augmented matrix into an upper triangular or row echelon form. Third, examine the ranks of the coefficient matrix and the augmented matrix to determine whether a solution exists and whether it is unique. If the system has an appropriate solution, we then convert the triangular matrix back into a triangular system of equations. Finally, we use back substitution. This means we solve the last equation first, then substitute that value into the equation above it, and continue upward until all variables have been determined. Gaussian elimination is one of the most widely used methods because it can be applied to many different types and sizes of linear systems. Now let us apply the Gaussian elimination method to a specific system of three linear equations. We begin by writing the coefficients and the right-hand side values in an augmented matrix. The first row is 1, 2, 0, and 1. The second row is 2, 1, 1, and 0. And the third row is -1, 6, 3, and 1. Our first goal is to eliminate the entries below the first leading entry. We keep row 1 unchanged. Then, replace row 2 by row 2 minus 2 times row 1. This gives 0, -3, 1, and -2. Next, replace row 3 by row 3 plus row 1. This gives 0, 8, 3, and 2. At this stage, the entries below the first pivot are 0. We can now continue the elimination using the second row. Now we continue the Gaussian elimination process from the previous slide. We start with the matrix obtained after eliminating the first column. First, keep the first row unchanged. Next, divide row 2 by -3. This gives row 2 equals 0, 1, -1/3, bar 2/3. Now use row 2 to eliminate the entry 8 in row 3. We replace row 3 by row 3 minus 8 times row 2. For the third entry, we get 3 minus 8 times -1/3, which equals 17/3. For the right-hand side, we get 2 minus 8 times 2/3, which equals -10/3. So the upper triangular system becomes x1 plus 2x2 equals 1, x2 minus 1/3 x3 equals 2/3, and 17/3 x3 equals -10/3. Now use back substitution. From the last equation, we obtain x3 equals -10/17. Substituting this into the second equation gives x2 equals 8/17. Finally, substituting x2 into the first equation gives x1 equals 1/17. Therefore, the unique solution is x equals the column vector 1/17, 8/17, and -10/17. Since the coefficient matrix and the augmented matrix both have rank 3, equal to the number of unknowns, the system has a unique solution.